this computer. I will share my screen. Then we'll sit here and we'll wait for the screen to pop up. There it is. Fabulous. All right, so it's been a while, huh? A few days. So last time we spoke was last Friday, and today is Wednesday. And so it couldn't hurt for me to, as usual, give you a little bit of sense as to where the hell we are. So we were talking about the Ising model. Oh, what's going on? What's going on? Oh, I gotta screw in. There we go. Ising model, which is a model for the magnetization of materials as a consequence of the interactions between spins of the material's constituent electrons. Okay, and so again, just to remind you, we were talking about the Ising model, and we described what happens in various dimensions. So we're gonna work through what happens in 1D. And so 1D is where you have just a line with a collection of spins, electrons on the line. They are all equal distances apart, just to keep things relatively simple. So we have n of them. So we label which one they are with the index I. So 1, 2, 3, to n. They each have a spin that's associated with them, which because they're electrons and the spin is quantized, it can only be either up or down. So we assign a variable called sigma to each one of these spins. So we call it sigma I, which tells us the orientation of the resulting magnetic dipole moment of the electron. So for example, if this electron has its magnetic dipole moment vector pointing up, we would say that this one is equal to +1. And if it has its magnetic dipole moment vector pointing down, we would say that's equal to -1. Okay, so now the benefit of doing this in 1 dimensions is that it's relatively easily tractable. And we're going to be able to actually explicitly work through this thing in excruciating detail with essentially every possible, with external field, without external field, with spin-spin interactions, without spin-spin interactions, and then just in general, with everything thrown in all together, we'll be able to do it. It's not so bad. The downside is it does not actually explain magnetism, right? So the problem with doing it in 1 dimension is that this thing does not exhibit phase changes. Specifically, if we look at the magnetization of this thing, where the magnetization is defined to be the average magnetic moment of the material, like so. And you can write this as mu times the average set of spin orientations, which another way to write this is mu times the average sum over all the spins, like so. So now, so this is the magnetization. And specifically, if you want to explain magnets, what you have to do, so this thing is a function of the applied external magnetic field, B, and the temperature, T. And if you want to explain magnets, what makes a magnet is that even when it's not in a magnetic field, it still has a magnetic field, still has a magnetization. Specifically, what we need to explain magnets is to calculate the magnetization when the applied external field is 0 at some finite temperature. And so now the problem, as we're going to see today, is that in 1 dimension, this thing is 0. There is no spontaneous magnetization because you can't have phase changes in 1 dimension. To get phase changes, you have to work in 2 dimensions. Okay, so phase changes show up in 2 dimensions, and that is where you have a lattice of spins. And I think the shape of the lattice can be arbitrary, so whether it's a rectangular lattice like this or hexagonal or whatever the hell you want, you can still get essentially the same results. And so what happens is at each vertex of this lattice, you put a spin. And then, for example, when you look at the spin-spin interaction, so say we're interested in this electron at any given moment in our sum, then the interactions you would have to take into account when considering that spin is the interactions between all nearest neighbors, which would be these four guys. And so when you perform this sum in your Hamiltonian, that I'm going to write down explicitly here in a second, then you have to sum over four nearest neighbors instead of just two like you do in one dimensions. So the good thing about this is that in 2D you do get phase changes, so it does explain spontaneous magnetization of materials. The hard part is that it's hard, right? So like I told you last time, the first guy to do this was Lars Onsager back in like 1920s, 1930s, something like that. And the man was he was a mentat, right? He made Lars Onsager makes Paul Dirac look like Richard Feynman, I think is the way to put it. Okay, so it's really hard, really hard. We're not going to be able to do it. All we're going to be able to do is essentially sketch the outlines as to what it looks like. So we're going to talk about phase changes and what they look like when you analyze models like this, but that's about it. And the Ising model still hasn't been solved in 3D, so we're not even going to try working it in 3 dimensions. Okay, so let's get to it. So last time, what we did was we wrote down our Hamiltonian for the Ising model. And we wrote this down so many damn times. You'd think I'd be able to just write it down now. I think I can. Let me try it. So we have J, Ij, sigma I, sigma J, sum over nearest neighbors. So these pointy brackets indicate the sum is just over nearest neighbors in order to keep the thing tractable. Okay, so this term here describes the spin-spin interactions. And then if we apply an external magnetic field, which in general you can do, then the term for the external magnetic field looks like, again, if I can remember correctly, I believe it looks like this. There we go. And so this term gives us spin external field interactions. Okay, and what we did last time was to take this Hamiltonian and write down the general form of the partition function, right? So now you take this Hamiltonian, you stick it into the usual formalism for calculating the partition function, and what we wound up with was this. Let me just write down what the answer was. So you got to sum over all orientations of sigma 1, either up or down. Sum over all orientations of sigma 2, either up or down, yada, 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 all the way up to the last spin. And then it is exponential of beta j, sum over nearest ij, sigma I, sigma j, plus beta mu b, sum over I, sigma I. All right, so I believe, and then, so that's the partition, the general form of the partition function. Then once you have the partition function, then you can calculate the free energy. And the free energy is just minus inverse beta log z. Okay, and then once you have the free energy, you just start taking derivatives in order to calculate expectation values of your system. All right. Okay, so now in going from here, from our Hamiltonian to here, our partition function, specifically, I made the assumption that this spin-spin interaction parameter J, which is a matrix, is the same for all interactions. So it's the same constant for all interactions. That's why it's written as J instead of Jij, and I pulled it through the sum. Everything else, I believe, is relatively straightforward here. All right, so we good? Good. Okay, so now, what we're going to start doing today is working this problem to see how this thing behaves. And like I said on Friday, there are three special cases we're going to work through. So the first special case is the non-interacting model. That is where J is equal to 0. And if J is equal to 0, you can see from our Hamiltonian that kills our spin-spin interaction term. And so the only thing that's happening is that the individual spins are interacting with the applied external field. The second case we're going to work through is the zero field model. That is when B is equal to 0. So the only thing that's happening is spin-spin interactions. And then for the grand finale, we are going to do the general model, or the general solution of this thing, where both J and B are not equal to 0. The math gets a little bit more hairy, but we'll be able to do it. All right, so shall we? So first, let's start with the non-interacting model. That is J is equal to 0. All right, so if we write down our Hamiltonian for J equals 0, all we've got left is mu B sum over sigma I. Okay, and that's, that looks relatively straightforward to do. Now, notice one thing. So in other words, the energy of the system, so you could also say this is equal to the energy of the system, only depends upon the interactions of the individual spins with the applied external field. They're not talking to each other, only to the external field. Now, one thing we're gonna go through the whole business. We're gonna calculate the partition function. We're gonna calculate the free energy. We're gonna start taking derivatives. We're gonna find the magnetization. We're gonna see how this thing behaves. One of the things we're gonna calculate is the average energy. Okay, so one of the things we want to calculate is the average energy. And starting with this as our Hamiltonian, you can say that this is equal to the average of minus mu B sum over the spins. Now, mu and B are constants by definition, right? Because we got a constant applied external field. The magnitude of the dipole moment vector for each spin is a constant. The only thing that changes is its orientation. So these two jobbies here are constants, which means, the average of a constant is just a constant. So you can pull that through these brackets. And so you will see that we just write this, well, even more suggestively, let me write it like this. B, no, God, what am I doing? Parentheses, mu, average, sum over, average of the sum over the spin. Look at this. What is this? That thing is the magnetization, right? So this dealy here is the magnetization. So let me make sure I'm not doing anything dumb here. Okay, very good. So this is minus B times the magnetization. Okay, so in other words, once we find the magnetization, we also find the average energy, and vice versa. If we find the average energy, we also know the magnetization. Okay, so just to be super explicit, we have this relationship right here. Okay, so now let's do it. So now the first job in calculating any kind of expectation value in statistical mechanics is, let's get our partition function. All right, so if this is our Hamiltonian, then our partition function is just this. Okay, so it's a partition function for n spins, and it's just the sum over all possible spin configurations of e to the minus beta h. Okay, and h is this thing I just wrote up here. So you just substitute that in. Sum over spin configurations. So it's e to the So now we got a minus sign here. We got a minus sign here. So those are going to go away. And we get e to the beta mu b sum over spins. Okay, so this thing, this dealy here, it looks like e, if I just write it out explicitly, it's e to the beta mu b spin 1 plus spin 2 plus spin 3 plus spin n. Okay, so I have an exponential of a sum in my exponent. An exponential of a sum in the exponent is the same as a product of exponentials, right? So I can write this as sum over all spin configurations, product of all spins, e to the beta mu b sigma I. Okay, so what we have a sum over a product. So in other words, we write out our product for one spin configuration, then we add on our big long product for another spin configuration plus another. We add on another product of all of our spin configurations. So we're going to get a long series of sums of products of exponentials. Now, because these exponentials are not talking to one another, that is, in each exponential only has one of the spins in it. That means that whether you take the sum first or you take the product first doesn't matter. You'll get the same thing regardless. All right, so in other words, what I can do is, so now I'm taking the sum of a product. You get exactly the same thing if you take a product of sum. So in other words, I can swap these two, I don't know what you call these things out front, operators? Not sure. I'm going to write this now as just product from I equals 1 to n. And then I sum e to the beta mu b sigma I. And now the nice thing is when you do this, so now essentially you're taking care of each individual spin configuration. The responsibility for that now has essentially been drafted into this product operator. So now when you take the sum, instead of having to sum over all possible spin configurations, now all you have to do is just sum over the possible values of each individual spin. Okay, so in other words, what you do is you just sum over sigma I is equal to either plus or minus 1. And that's easy, right? We can do that. Okay, so now these two things, again, you just swap your sums and products, you get the same thing. Okay, now, hey, look at this thing. Get rid of that. So now let's focus our attention on this sum here. And man, that just couldn't be any easier, right? So I mean, our possible values for sigma I are just plus and minus 1. So when we take this sum, all we have to do is just substitute in plus and minus 1. Piece of cake. Okay, so if I do that, what I get is this is equal to the product from I equals 1 to n. And then I just do the sum, right? So I plug in sigma I equals plus 1, and I get this, e to the beta mu b. Okay, and then I plug in minus 1, and I get plus e to the minus beta mu b. Look at that. Lovely. Okay, so now let's, again, come with me on a mathematical journey, won't you? So if we focus on this thing, what is this? Okay, so you guys might be familiar with cosine theta. You can write as exponentials, right? So you can write cosine of theta as e to the I theta plus e to the minus I theta over 2, same thing. And so now it turns out that that looks a whole lot like what we've got up here. Somebody's saying something. Yes, so Indy says, would this be hyperbolic cosine? Yes, my good man. See, I told you, your precognition powers are already starting to develop. I'm so proud of you. Okay, so cosine is just a sum of imaginary exponentials. So what we have is exactly the same thing, except it's real. Okay, and so that's as the gentleman said, that's a hyperbolic cosine. So the hyperbolic cosine is exactly the same thing as the cosine. It's just real, right? So it's e to the theta plus e to the minus theta over 2. So that looks a whole heck of a lot like what we've got there in our product. Okay, so we can write this as pi, so the product from 1 to n of hyperbolic cosine of mu b, like so. And then you'll notice in the definition of hyperbolic cosine, we've got this extra factor of a half, which we don't have in our partition function. And so to take care of that, we have to multiply by 2, like so. And there it is. So now what you have, you just have, so now this thing doesn't have any i's in it, right? There's no more i's. It's just 2 cosh mu b. And then what we have is just a product of n terms of that. So in other words, when you take this product, what you're going to get is just 2 to the n cosh mu b to the n. That's it. So here is our partition function. That just could not be prettier, right? I mean, you start out with some god-awful looking sum, and you wind up with, this lovely closed form. It's just one term, man. It doesn't get any prettier than that. Okay, so there is our, did I forget a beta somewhere? I did. Let's have betas in it too, like that. Okay, that's right, right? Right. Okay, so there's our partition function. So now we have a partition function. The next thing we calculate is our free energy. So the free energy is just minus 1 over beta times the logarithm of this thing. And so this is minus, oh, don't get too fancy now here, Professor. Minus cosh, 1 over beta times the logarithm 2 to the n cosh to the n beta mu b. So there it is. So I could just write this as, let me write this in the following way. Like so, right? So I essentially just factor that exponent out. So I just have a, within the brackets raised to the power n. And now, because of the lovely properties of logarithms, I can take that exponent and pull it out front. So I get minus n over beta logarithm 2 cosh beta mu b. There it is. Okay, so that is our free energy. Shazam. Okay, so now we got our free energy. The way that you start extracting information from your free energy is you take derivatives. So the first thing let's do is let's calculate the average energy. Okay. The average energy okay, so that's what I'm going to call E. So E is just equal to the average or the expectation value of the Hamiltonian. This is, by definition, equal to this, the Hamiltonian, times your probability distribution of the Hamiltonian, which is just the Boltzmann weight, divided by the partition function. And so that you can see written in this very general form that in order to get this factor of H down in the numerators to calculate your expectation value, what you do, so up in the exponential, the H is multiplied by beta. And so in order to calculate the average of the Hamiltonian, all you have to do is take your free energy and differentiate with respect to beta. Okay, so this is equal to minus dd beta log Zn, okay, which, you know, that's essentially our free energy. Okay, and this is equal to minus dd beta logarithm of our partition function, which is, okay, I'm going to write exactly what I have in my notes because it's not a good idea to get overly clever while you're doing things in the spur of the moment. So I'm just going to write it to the n cosh to the n beta mu b. Okay, there it is. Okay, so now we take the derivative of this logarithm with respect to beta. All right, so chain rule out the wazoo, right, my friends? So the first thing you do when you take the derivative of a logarithm is you get a 1 over the argument of the logarithm. All right, so the first thing you get is 1 over 2 to the n cosh to the n beta mu b. 1 over that. Okay, then, again, I'm not going to get too fancy. I'm going to write exactly what is in my notes. Then we have to take the derivative of 2 to the n cosh to the n beta mu b. Okay, so 2 is a constant. We can do that. You just pull the 2 through. And so that this 2 is going to cancel with that 2 down there in the denominator. Derivative of cosh is, in fact, sinh. All right, so we're going to get minus cosh n to the n beta mu b in the denominator. When we take the derivative of this thing, we're going to get a factor of n from pulling down the exponent. We're then going to have cosh to the n minus 1 beta mu b, like so. Then you take the derivative of the cosh, and that gives you a sinh. And then you have to take the derivative of the argument of the cosh, which is the beta mu b, and so you just get a factor of mu b. All right, so there it is. Not so bad, right? Okay, so now you can see, so what we have down here in the denominator is cosh to the power of n. And what we have up here in the numerator is the same cosh. It's the same argument, beta mu b. We just have n minus 1 of them instead of n of them. So what's going to happen is that this is going to cancel with all these and just leave us one factor of cosh in the denominator. And so if we clean this thing up a bit, what we get is minus n mu b times sinh beta mu b over cosh beta mu b. And you, oh my God, what is that? My nerd senses are tingling. This looks so similar to something I've seen before, right? I know that sine over cosine is tangent. This looks so familiar. It's just sinh over cosh instead of sine over cosine. So guess what? It's the same relationship. This is tanh. Tanh, beta mu b. So that is our average energy. Lovely. All right, so everybody cool? Like a Zoom meeting full of Fonzies. Excellent. All right, so now we have our average energy. And as we described when we started back here, once you know your average energy, you also know your magnetization, right? Because our Hamiltonian now is so simple that when we calculate our average Hamiltonian, that gave us just this, that the average energy is just the magnetic field minus the magnetic field times the magnetization. All right, so if we go back down here, we know that the average Hamiltonian is minus magnetic field times the magnetization. And hence, our magnetization is minus average Hamiltonian divided by B. Okay. And that is N mu tanh beta mu B. There it is. Fabulous. And you can see that the magnetization is proportional to the magnetic dipole moment of each individual electron, right? So this makes sense. Each individual electron acts like a magnet with strength mu. And so what this says is that each electron acts like a magnet. You got N of them, so the total possible magnetization is just N times mu, which makes sense. And then the magnitude of the magnetization is modulated by this tanh function. All right, so now you got to think, what the hell does tanh look like? Well, yeah, they don't make just anybody a professor. I know what tanh looks like. If we draw it, it looks like this. Okay, so on my axes here, my y-axis is going to be the magnetization. And my x-axis, just to keep things simple, is just going to be beta mu b, right? It's just the argument of my tanh. Okay, so, and you know, we're going to assume we work at fixed temperature, so beta is just some constant. Mu, again, that's just the strength of each individual electron's magnetic dipole, so that's a constant. The only variable here is just b. But, you know, just to make the drawing easy, I'm going to have the x-axis as beta mu b. Okay, so now what does this thing look like? Okay, so like I said, the maximum possible values of this thing are N mu. Okay, so that's when tanh is equal to 1. The magnetization is equal to N times mu. So let me draw some dotted lines. So tanh can also be equal to -1, right? So then we come down here. So when tanh is equal to -1, it's down here. So that's minus N mu. There it is. And now you just draw what the tanh function looks like. And it looks like this. Okay, here we go. Let's see if I can do this without screwing things up. So it looks like a sigmoid, right? So it looks, you know, looks like that. It looks like that. So when the magnetic field is strongly negative, right? That is when when you're over here, the magnetic field is negative, pointing down, and it's very strong. That causes all the spins to line up with it and point down. Okay, and so when your field is strong, pointing down, all of your spins are going to line up with it, and they're all going to point down, such that the net magnetization is just minus N times mu. That is, all of your electrons are pointing down. As you weaken the magnetic field, right? So now you weaken the magnetic field, so the spins, they start jiggling a bit. I mean, because of temperature. What the temperature corresponds to is fluctuations in the spin. And so as the strength of the magnetic field weakens, then the magnetic field is no longer strong enough to suppress those fluctuations, and so they can start just spontaneously flipping. Okay, to the point where when you get to 0 applied magnetic field, then because they're not interacting with one another, you're just as likely to find them due to thermal fluctuations flipped either up or down. And so on average, they cancel out and you get 0 net magnetization. And then as you start ramping the field up in the positive up direction, the opposite starts happening. So they're fluctuating, and as the field gets stronger, they go, oh, I like that. And they start lining up with the field until, once the field is strong enough in the positive direction, they all line up jazz hands, pointing up, right? Okay, so now you might, from that description, between, say, like here And here, when the spins are subject to thermal fluctuations in order to determine their average orientation, you might expect that the width of this regime depends upon the temperature, right? Because the higher the temperature, the more thermal fluctuations you get, and therefore the wider this region is going to be. You'd be exactly right. Okay, so if we calculate the slope of this function at external field equals, well, it's not, if we just calculate the slope of this function, okay, so we're going to take the magnetization, and then we take the derivative with respect to, I believe the way this is defined is with respect to mu b. That will give us the slope of this function. And then if you take this derivative and you just divide it by the number of electrons that you have, this is what's defined to be what's called the magnetic susceptibility. Okay, and all the magnetic susceptibility is, if you remember your E&M classes, so if you apply, I think the definition is related to, so it looks something like this. You apply an external magnetic field to a material. That applied external magnetic field induces a magnetization. So the applied external magnetic field gives you a magnetization, and the constant, there's a proportionality constant between these two. That's the magnetic susceptibility. All right, so in other words, the magnetic susceptibility is a measure of how easy it is to magnetize a system. In other words, it's the slope of this function. And so now if you take our magnetization, which is this tanh, and you take the derivative with respect to mu b, then what you get is beta 1 minus tanh squared beta mu b. Okay, and you can see that it does indeed depend upon beta, the temperature. So the smaller the temperature is, the more narrow that range is going to be. Okay, that is the steeper the slope, because it's going to go. Okay, so if the temperature is very low, you expect that slope to be very large, which is because it's proportional to beta. That's what's going to happen. If the temperature is very large, you expect that region to be wider. And again, that's exactly what happens. It gives you a smaller slope. Okay, does that make sense? More or less? Wunderbar. All right, so that is a magnetization with zero interactions. Okay, so all that's happening is we apply an external magnetic field, and the spins line up with the field in whatever direction it is the field is pointing, and you get some smooth transition between the two possible extremes. So yeah, if you guys went and you looked up the YouTube video of a frog being placed in a magnetic field, this is what happens, right? Everything, if you put it in a strong enough magnetic field, will become magnetic. Okay, and if you go look up YouTube for the frog in a magnetic field, you'll see that they put a frog in a really strong magnetic field. It turns into a magnet, and the frog starts floating around. It's really quite dramatic. Okay, so that was number one, no interactions. Now, number two, we're going to get started on. I'm not sure if we're going to we'll try to finish it in 10 minutes. If we don't, no big deal. We'll just come back and we'll finish it on Friday. Okay, so number two is going to be the zero field model. That is when we don't apply any external field and we only rely upon spin-spin interactions to generate any kind of magnetization for our material. Okay, so again, our general Ising Hamiltonian was this minus J sum over nearest neighbors, sigma I, sigma J, minus mu B sum over individual spins. Okay, so now we're looking at 0 applied external field. What that means is, oh no, I missed. Oh, I missed. There. So that's our Hamiltonian with, oh, somebody's got something to say again. There it is, link for the, so Eric went and found the magnetic frog. Thank you, sir, I appreciate that. So he posted the link to the floating frog in the chat window, so I recommend you go check that out if you like. Seems like you're paying attention during the lecture. Go and looking at YouTube. Very good. All right, but I digress. This now is our Hamiltonian with 0 field. So the only term we have is the spin-spin interaction term. Okay, now I can also write this in this way. So instead of writing this sum as a sum over nearest neighbors, what I can do is write it like this. I just sum from I equals 1 to n minus 1 of sigma I plus 1, right? So now what that does is I picks out a spin, the I plus 1 gives me the spin right next to it, so that term is the contribution to those two little guys. And then when I move on to I equals 2, then I stick with this little guy and I add up the spin on the other side, and I just keep doing this all the way down the chain. All right, but now what we get for this sum depends upon what we choose for our boundary conditions in this particular case, because again, our lattice that we're summing over is just a one-dimensional chain of spins. All right, so we're going to start here at I equals 1, and then we're going to go all the way down here to I equals n, and then the question is, what happens when we get to I equals n? Do we stop? Do we have them wrapped around in a circle so that we go back to where we start? What do we do? And what you do, you'll get generally the same behavior regardless of what you do, or at least certainly in the middle of the chain you will get the same behavior. You'll only get funky things happening at the edges depending upon what you choose as your boundary conditions. So now what we're going to do here for just to see what happens, we're going to use what are called free end boundary conditions, or BCs. And so I've essentially already indicated that I'm doing that by what I'm doing is I say when I take the sum from I equals 1 to n minus 1, I'm saying that I'm going to stop right here at n minus 1, and the last term in the sum that I deal with is those two guys. In other words, I don't move on to the next guy because there is no next spin. Okay, so when I wrote down this sum, I already assumed I was doing free end boundary conditions. All right, everybody good? All right, so if now I wrote out explicitly what my Hamiltonian looked like, it would look like this. Minus j times sigma 1, sigma 2, plus sigma 2, sigma 3, plus sigma 3, sigma 4, plus dot, dot, dot. And then the last term I'll get is sigma n minus 1, sigma n. So that's the Hamiltonian. Okay, so now what you do is you take this Hamiltonian and you stick it into an exponential in order to calculate the partition function. But it turns out that just leaving it like this is kind of a mess. And so what we're going to do is we're going to change variables. So let's make a coordinate transformation to make this easier. Okay, so the variables I'm starting out with here are just my spins, right? So my variables I start with are just my various spins. And I'm going to change these variables to something else. And what they're going to look like is this. So I don't touch the first spin. The first spin is still the same. But everything else, I'm going to make a new variable called P. All the way up to Pn. Okay, so what is P, you ask? So I define P. So for example, P2, I define as sigma 1 times sigma 2. P3 is sigma 2 times sigma 3. All the way up to Pn. Pn is sigma n minus 1 sigma n. Okay. So in other words, these P's are just the products that you find in the Hamiltonian when you write it out explicitly. Now, think about what these variables look like. What does P look like? Say what one more time. Okay, so again, the sigmas can only take on a value of either plus or minus 1, right? So if the spins are both pointing in the same direction, okay, so if, for example, sigma 2 and sigma 3 are both pointing up, so they're both plus 1, then that means that P3 will be equal to plus 1. If they're both pointing down, they're both minus 1, you will still get P3 is equal to plus 1. It's only if the spin switches. Okay, so you go up to sigma 2. If the spin flips from sigma 2 to sigma 3 in either direction, then and only then does P3 equal minus 1. So in other words, what this P variable indicates for you is whether or not the spin is flipping at that site. Okay. So in other words, the allowed values for sigma I are plus and minus 1. Same is true of the P sub I. They are also equal to plus or minus 1. And whether it's plus or minus 1 depends upon not the spin, but whether or not the spin is flipping from one site to the next. Okay, does that make sense? Okay, then the Hamiltonian, we can write the Hamiltonian in terms of this P variable very easily. Now it is just this. Voila, that is the Hamiltonian, piece of cake. So now you just sum these P variables from 2 to n, okay? And so now this is our Hamiltonian. We take that Hamiltonian and we stick it into our partition function, where we sum again over all, whoops, we're not summing over spins anymore, we're summing over P configurations. And we have 1 minute left. So what's going to happen here is extremely similar to what we did for the zero field configuration, because if we go back up here to our zero field, you can see it looks very similar, right? It's going to be very, very similar. However, there is one little nuance which is sufficiently subtle that I don't think I can adequately explain it in the remaining 1 minute to my satisfaction. And hence, this is where we're going to stop today. And when we come back on Friday, we will finish working this zero field model, and then we'll move on to the general model where we have both field and spin-spin interactions, and it does get a little bit even hairier than this, okay? All right, so does anybody have any questions now at this point? Negative. All right, so that means that I'll see you on Friday, discussion section at noon if you choose to come. If you don't, that's fine too. And then our lecture is Friday at 4 p.m. usual time. So until then, adieu.